Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to imagine, just for a second, that you are an archaeologist.
Okay, I'm with you.
But you aren't, hacking your way through a dense, uncharted jumble somewhere. And you're definitely not sifting through the remote sands of Egypt.
Right, none of the Indiana Jones stuff.
Exactly. Instead, you are standing right in the middle of a bustling, hyper-modern, neon-lit metropolis. I mean, cars are just zooming by, massive skyscrapers are towering overhead, and there are millions of people rushing around in this chaotic symphony of modern life.
Sounds pretty overwhelming, honestly.
It is. But then right there, sitting completely unnoticed in the middle of a 12-lane superhighway, you spot something that is just flat out impossible.
An ancient artifact.
Yes. An absolutely pristine, untouched, mint condition Model T Ford, just, idling in the fast lane. Right. It's completely out of place among all the electric vehicles and the hyper-modern infrastructure. It really shouldn't be there at all. It belongs to an entirely different era. But there it is, just hiding in plain sight. And if you pop the hood, the engine block actually holds the very engineering secrets of how the first factories were ever built.
That visual, the whole anachronism of it, it maps perfectly onto the reality of what we were looking at in this deep dive today.
Yeah.
Because we're dealing with an object that frankly, fundamentally breaks the timeline of its surroundings.
It really does.
Yeah, it's a relic from the absolute beginning of history. It's preserving a state of the universe that's supposedly vanished, over 13 billion years ago.
13 billion years. It's staggering. We are tracking down the ultimate cosmic relic today, the most pristine star ever found in the known universe.
And it has a very catchy name, too, right?
Oh, the catchiest. It has a deeply unglamorous catalog name, SDSS J0715-7334. But the single faint point of light is that exact Model T Ford on the galactic superhighway.
Hiding in plain sight.
Exactly. So today we're going to explore the mechanics of what actually makes a star truly pristine, We'll get into the massive automated technological ecosystem that was required to even locate it.
That is a story in itself.
Huge story. And maybe my favorite part, the incredible human element, the undergraduate students who actually cracked its chemical code while on a spring break field trip.
It's just such a great narrative.
It really is, because when you step outside and look up at the night sky, you aren't just seeing lights. You are looking at a multi-generational family tree of stellar evolution. You've got, parents, grandparents, highly complex descendants up there. And today we are meeting the ultimate ancestor.
To really grasp the mechanical improbability of SDSS J0715-7334 surviving all the way to the present day, we kind of have to rewind the clock.
All the way back.
Right, all the way back to the era immediately following the Big Bang. Specifically, this period we call the Epoch of Recombination.
Okay, so set the scene for us. What does that look like?
So we are talking about a period roughly 380,000 years after the initial expansion. That is when the universe finally cooled down enough for the ambient radiation to drop below the ionization threshold of hydrogen.
That's the moment the fog finally lifted, right?
Exactly, the fog lifted. Because before that point, the universe was essentially this opaque plasma. Protons and electrons were just zipping around with so much kinetic energy they couldn't bind together.
Like a hyperactive mosh pit.
That's a good way to picture it.
Mm-hmm.
And any photon of light that tried to travel through that mess would just instantly scatter off a free electron. The universe was effectively this blinding, superheated soup.
You couldn't see anything, even if you were there.
Right. But as space expanded, the thermal energy of those particles began to drop. And once the temperature dipped below about 3,000 Kelvin, something crucial happened.
They slowed down enough to stick.
Exactly. The electrostatic attraction between the protons and electrons finally overcame all that kinetic energy. They snapped together and they formed the very first neutral atoms.
And those first atoms were incredibly basic, right?
Extremely basic. They were almost exclusively hydrogen with, a smattering of helium and just a negligible trace of lithium.
Mm.
And that was it. That was the entire periodic table at that moment.
No carbon, no oxygen, no iron.
Nothing. Just a vast cooling ocean of neutral gas. slowly settling into what we call the cosmic dark ages.
Which sounds ominous, but it's really just the stage being set, because out of that pristine, incredibly simple gas, gravity had to somehow figure out a way to build the first generation of stars, what your astronomers call population 3 stars.
Right, population 3. And the thermodynamics of that building process are incredibly hostile to star formation.
Why is that?
Well, for a cloud of gas to collapse into a star, gravity basically has to win a tug of war against thermal pressure. When you compress gas, it heats up. Everybody knows that, right?
Right, like pumping up a bicycle tire. The pump gets hot.
Exactly. So if that gas cloud can't radiate that newly generated heat away into space, the thermal pressure pushes back against gravity and the collapse just halts. It stops dead.
So it needs a way to cool down while it's collapsing.
Yes. In the modern universe, gas clouds contain heavier elements: carbon, oxygen, silicon. And these elements are fantastic coolants.
How do they cool things down in the vacuum of space?
Their atomic structures are complex, so they allow them to easily absorb kinetic energy from all the particles colliding around them, and then they radiate that energy away as infrared light.
Okay, so they act like thermal exhaust vents for the gas cloud. They let it cool down, lose that outward pressure, and then gravity can keep crushing it together.
That is a perfect analogy, thermal exhaust vents. But here's the problem. Those first population 3 stars, they didn't have heavy elements.
Right, because nothing had made them yet. They only had hydrogen and helium.
Exactly. And molecular hydrogen is an incredibly inefficient coolant. It's terrible at it. So the only way gravity could overcome the fierce thermal pressure of that pristine gas was through sheer overwhelming mass.
It just had to brute force the collapse.
Yes. The physics essentially required these first-generation stars to be absolute behemoths. We are talking hundreds, perhaps even 1,000 times the mass of our modern sun. That was the only way to force the gas to collapse enough to ignite nuclear fusion.
So the gravitational crush just had to be immense to trigger that ignition, and because they were so massive, their core temperatures would have been, unimaginably high.
Off the charts. And a star's lifespan is entirely dictated by the temperature of its core. A massive star doesn't just burn its fuel, linearly faster than a small star. It burns it exponentially faster.
It's like a gas-guzzling supercar compared to an economy sedan.
Exactly. The extreme pressure in a population 3 star would have forced its hydrogen fusion process to just run at maximum capacity constantly. It had to do that just to maintain hydrostatic equilibrium.
Hydrostatic equilibrium being the balance between gravity crushing it and fusion pushing out.
Right. So to maintain that balance, they burned incredibly fast. They lived incredibly brief, violently energetic lives, and they exhausted their fuel in just a few million years.
Which, in the lifespan of the universe, is a cosmic blink of an eye.
Not even a blink. And when they ran out of fuel, that outward pressure from the fusion just stopped. Gravity won the tug-of-war instantly, and the core collapsed.
Resulting in supernovae, right?
Core collapse supernovae, yes. Or
Right.
even parent stability supernovae, which are so violent they completely obliterate the star without leaving even a black hole behind. Just total destruction.
Wow. Total obliteration.
But the really crucial mechanic here, for our story, is what happened in the moments leading up to and during those massive explosions.
The alchemy part of it.
Yes. The intense pressures and temperatures inside these dying behemoths acted as stellar forges. Through a process called nucleosynthesis, they smashed helium atoms together to make carbon.
Okay.
And then they fused carbon to make oxygen. Then neon, silicon, all the way up the periodic table to iron. And then the explosion itself synthesized even heavier elements and blasted all this newly forged material out into the pristine cosmic ocean.
So they essentially seeded the universe with the very first heavy elements, the first pollution, basically. And actually, this brings up that terminology quirk we should probably address because it definitely changes how we have to read the data later on.
Yes, the astronomer's definition of metals.
Right, because in astrophysics, the periodic table is basically divided into 3 distinct things: hydrogen, helium, and everything else. And everything else gets grouped into one single word.
Metals. Yeah, to an astronomer, literally anything heavier than helium is a metal.
Which is so confusing for the rest of us.
I know. Oxygen is a metal, carbon is a metal, neon is a metal. It's an archaic naming convention from the early days of spectroscopy, honestly.
Yeah.
But it still serves a very practical mathematical purpose for us.
How so?
It allows astrophysicists to define a star's composition using just one single parameter, metallicity.
Got it.
So those population 3 stars we just discussed, they were completely metal-free, zero metallicity.
Yeah.
They manufactured the first metals and then scattered them.
Which then sets the stage for the second generation of stars, population 2 stars. They form from gas clouds that have been slightly polluted by the shrapnel of those first supernovae. And that brings us to our star, SDSS J0715-7334.
Exactly. It is a second-generation star.
It formed right out of the immediate wreckage of those first massive explosions, which makes it, over 13 billion years old?
Right around there, yes.
Okay, wait. I'm doing the math in my head here, and I'm seeing a gaping structural contradiction in what we just talked about.
Uh-oh. Lay it on me.
You just laid out the physics. A star forming from metal-free, or nearly metal-free, gas has to be incredibly massive to overcome thermal pressure because it doesn't have the thermal exhaust vents.
Correct.
And because it's massive, it burns extremely hot and blows up in a few million years. So if SDSS J0715-7334 formed in an environment with almost no metals, why didn't it blow up 12.9 billion years ago? How is a 13 billion-year-old low-metal star still sitting there, quietly fused in hydrogen today? It shouldn't exist.
That paradox right there. That is exactly why this star is considered a holy grail in astrophysics. You've hit the nail on the head. Its mere existence challenges the standard models of early star formation.
So what's the workaround? How did it survive?
The answer lies in the highly localized mechanics of those first supernovae. When a massive population third star exploded, it didn't just passively scatter metals, it generated massive violent shock waves.
Okay, shock waves.
And these shock waves slammed into surrounding uncollapsed clouds of that pristine gas. The mechanical compression from the shock wave forced the gas together so rapidly that it basically bypassed the thermal pressure bottleneck entirely.
Oh, wow. So the shock wave did the work that gravity couldn't do alone.
Exactly. It forced the gas to fragment into much smaller clumps before it ignited. And this allowed the second generation of stars to form with significantly lower masses, even without the cooling benefits of those heavy metals.
That is wild.
It's incredible. So SDSS J0715-7334 is a low-mass star. It's actually likely less massive than our own sun. And because it has such low mass, its core is under far less gravitational pressure.
So it doesn't have to burn hot to fight back.
Right. The nuclear engine at its core only have to, idle to push back against gravity. It just sips its hydrogen fuel at an incredibly slow rate.
So while its massive first-generation parents redlined their engines and exploded in millions of years, this tiny low-mass descendant has just been quietly simmering on low heat for the entire history of the universe.
Simmering, yes, and preserving the exact chemical fingerprint of the gas cloud it was born from. That's the key.
Wait, how does it preserve it? Doesn't the fusion in the core mess up the chemistry?
You'd think so, but no. The outer envelope of a low-mass star doesn't actually mix deeply with the nuclear furnace down at its core. The surface layers remain a pristine, unadulterated sample of the environment present just moments after the first stars died.
So it really is a true cosmic fossil record.
A perfect time capsule.
Well, let's get into the actual anatomy of this fossil, because the measurements of SDSS J0715-7334 are pretty mind-bending. When we say this star is pristine, we are talking about a fractional trace of metals that borders on undetectable, right?
Yes. Extremely minute quantities.
It has less than 0.005% of the metal content found in our modern sun. Less than 0.0005%.
It's almost nothing.
It is twice as metal poor as the previous record holder. But the most important metric, the one that really blew people away, is its iron content. It is a staggering 40 times more iron poor than the most pristine star previously documented in astronomical catalogs. 40 times.
Yeah, that iron scarcity is the defining metric here.
Why iron specifically?
Because iron is the absolute endpoint of standard stellar nucleosynthesis. A star can fuse lighter elements together to release energy, right? Helium into carbon, carbon into oxygen. But fusing iron actually consumes more energy than it produces.
Which is a fatal flaw for a star.
Exactly. When a star tries to fuse iron, the energy output drops. Gravity wins. And that is what triggers the core collapse. Because iron is produced in such vast quantities by these supernovae, its abundance in a star's atmosphere acts as a highly reliable clock for cosmic evolution.
Like counting tree rings, almost.
Sort of, yeah. The more iron a star has, the more generations of supernovae preceded its birth. It's a measure of how polluted the gas was.
Which makes sense. I mean, our modern sun formed roughly 4.6 billion years ago, right? So it was born from a nebula that had been heavily enriched by thousands, maybe millions of supernova cycles over billions of years. It's a highly complex chemical stew.
Very complex.
Yeah.
So to find a star with an iron content 40 times lower than the previous extreme,
Yeah.
I mean, it means SDSS J0715-7334 formed from a pocket of gas that was almost entirely isolated.
Like a completely untouched bubble.
Exactly. It was touched by the ejecta of perhaps one single specific population 3 supernova, just one. And then the star locked that material away and hasn't changed since.
That's incredible. But there is another crucial chemical marker here that makes this discovery unprecedented, isn't there? Carbon.
Yes, the carbon anomaly is huge.
Let's dig into that, because usually when astronomers find extremely metal-poor stars, they are weirdly rich in carbon. Is that right?
You're exactly right. We call them carbon-enhanced metal-poor stars, or CEMP stars.
Absolutely.
Most of the ancient iron-poor stars we find have these surprisingly high ratios of carbon in them.
Why would they have so much carbon if everything else is missing?
Well, this led astrophysicists to hypothesize that early in the universe, carbon fine structure line emission, basically carbon radiating heat away, was the primary cooling mechanism that allowed these low-mass stars to form. The prevailing theory was that you absolutely needed an overabundance of carbon to cool the gas enough to make a small star like this one.
But SDSS J0715-7334 shatters that model entirely, doesn't it?
Completely shatters it. It has exceptionally low abundances of both iron and carbon. According to the carbon cooling theory, this star physically should not exist.
So what does that mean for the science?
Its mere existence forces theorists right back to the drawing board. It proves that other mechanisms, like that mechanical shockwave compression we discussed earlier, or perhaps dust-driven cooling pathways, were capable of forming low-mass stars in the very earliest epochs without needing high carbon.
It's tangible proof.
Exactly. We rely on these incredibly complex supercomputer hydrodynamic simulations to model the early universe. We input all the physics, we hit play, and we see what the simulation predicts a first-generation supernova should produce. But finding a physical star like this, it takes those models out of the realm of pure theory.
You can actually check the math.
We can look at the precise chemical ratios in its atmosphere and say, with confidence, this exact distribution of elements matches the nucleosynthetic yield of an asymmetrical explosion of a 60 solar mass population 3 star. It is empirical ground truth.
Which really highlights the monumental challenge of actually finding empirical ground truth in the first place. I mean, let's talk about the logistics of this. The Milky Way galaxy contains somewhere between, 100 and 400 billion stars?
That's the current estimate, yeah.
And the vast, overwhelming majority of them are modern, highly metallic stars like our sun. They are noisy, they are bright, and they are everywhere. So how do you find one single, faint, low-mass star with a 0.05% metal content hiding in a sea of hundreds of billions of heavy metal descendants?
Well, I can tell you, you definitely don't do it by peering through an eyepiece on your back porch and just getting lucky.
Right. It's a bit more involved than that.
Just a bit. You do it with industrial-scale, highly automated stellar demographics. The methodology here is amazing. It relies on an interconnected ecosystem of observatories operating in tandem, and the primary net, the big sweep, is cast by the Sloan Digital Sky Survey V, which is currently directed by the astrophysicist Juna Kollmeier.
Right, SDSS-V. And it's important to note this isn't taking pretty full-color pictures of nebulae for desktop background.
No.
It's a massive spectroscopic survey. They are taking the optical and infrared spectra of millions of stars simultaneously using these robotic fiber positioners.
Which is a monumental engineering feat in itself. But we need to explain how high-resolution spectroscopy actually extracts this information, because it's not intuitive.
Okay, lay it out for us.
Obviously, we can't send a probe 80,000 light-years away to scoop up some plasma in a jar and bring it back to a lab. We have to decode the starlight itself. When the light from SDSS J0715-7334 finally reaches Earth, it is a composite of every single wavelength emitted by its hot surface.
A full rainbow of light.
Right. But as that light passes through the star's cooler outer atmosphere on its way out, the atoms in that atmosphere absorb very specific frequencies of light.
Depending on the element, right? Like an electron in an iron atom will absorb a photon of a very specific wavelength to jump to a higher energy state.
Precisely. The physics of quantum mechanics dictates that an atom can only absorb exact, discrete packets of energy. So when you take that incoming starlight and run it through a spectrograph, you spread it out into a continuum, a rainbow. But wherever an atom in the star's atmosphere absorbed a photon, there is a dark gap in the spectrum.
An absorption line, or a Fraunhofer line.
Yes. And when you look at it, it literally looks like a highly complex barcode. The depth and the width of those dark lines in the barcode tell you exactly how much of a specific element is present in that star's atmosphere.
But capturing a high-resolution spectrum where you can measure the width of an absorption line down to, like, fractions of an angstrom just to detect a 0.005% metal trace, that takes significant telescope time, doesn't it?
Oh, an enormous amount of time.
You can't just spend hours exposing the sensor for every single star in the Milky Way. You'd never finish.
That's exactly the bottleneck. And this is why SDSS-V operates as the wide net filter. They use telescopes like the DuPont at the Las Campanas Observatory down in Chile and the Apache Point Observatory up in New Mexico. These telescopes take lower resolution spectra of millions of stars.
So they basically map the haystack first.
Yes, they map the haystack. Then they have algorithms scan the resulting millions of low-res barcodes looking for candidates that seem, well, unusually smooth. Stars that are conspicuously lacking the deep, distinct troughs where iron and carbon lines normally should be.
So the algorithms identify the anomalies. And once they have a list of targets that look highly suspicious, they hand those coordinates over to the heavy artillery for confirmation.
Exactly. And the heavy artillery, in this specific case, is the Magellan Clay Telescope. This is a massive 6.5-meter instrument, also located at Las Campanas in Chile. But the key isn't just the sheer size of the mirror gathering that faint light. It's the instrument attached to the back of it, the MIC spectrograph.
Right, Mike, which stands for Magellan Inamori Kyocera Echelle.
Yes. Echelle spectrographs are incredible.
Because they're a massive leap beyond just shining light through a simple prism, right?
Oh, absolutely. And Echelle grating is an absolute marvel of optical engineering. Think about it. If you just spread the light out in one long continuous band to get super high resolution, you would need a physical sensor that was literally meters long to capture it all.
Which is impossible to build or cool.
Right. So instead, an Echelle spectrograph uses a specially ruled diffraction grating to basically overlap multiple high-resolution spectra on top of each other. And then a second optical element, a cross disperser, separates them out vertically.
Okay, so it effectively takes an incredibly long, detailed barcode, chops it up, and packs it into a tightly stacked two-dimensional grid that perfectly fits onto a square digital CCD sensor.
That is exactly what it does, and the resulting resolving power is phenomenal. It allows astronomers to zoom in on the exact wavelengths where heavy metals absorb light and measure the tiniest, almost imperceptible dips in the signal.
So they can see the faintest traces.
Yes. And when they pointed the Magellan telescope at SDSS J0715-7334 and processed the data through the MIC spectrograph, the resulting spectrum wasn't just metal poor. It completely confirmed the star as the new gold standard for stellar purity.
The new baseline.
But, and this is where the story gets really crazy, the data analysis didn't stop at just its chemistry. They cross-referenced the star with astrometric data, which uncovered the most structurally bizarre aspect of this entire discovery.
Yes. The European Space Agency's Gaia mission. This is where it gets so cool. For context, Gaia is an observatory positioned out at Lagrange Point 2, far away from Earth, and its entire purpose is astrometry.
Precision astrometry.
Right. It precisely measures the positions, the distances, and the motions of over 1 billion stars in our galaxy with micro-arc-second precision. They literally map the exact 3D velocity vectors of these stars. And when they looked at the kinematics, the physical movement through space of our pristine little star, the vectors didn't align with the Milky Way.
It was a kinematic outlier, completely off book.
It was moving wrong.
Yeah. The tracking data charting its highly eccentric orbit allowed them to trace its trajectory backward through time. And it revealed that SDSS J0715-7334, which is currently residing roughly 80,000 light-years away in the Milky Way's halo, is an ancient immigrant.
It wasn't born in our galaxy.
No. The orbital mechanics point its origin all the way back to the Large Magellanic Cloud, which is a massive satellite galaxy that currently orbits the Milky Way.
Okay, wait. Let's pause and really think about this. Here's where it gets really interesting. It's one thing to find a needle in a haystack.
Sure.
It's another to realize the needle came from a completely different farm. This star was forged in the primordial gas of a completely different galaxy, survived for billions of years, and then was physically dragged across the intergalactic void into our own galaxy. How does the architecture of a star survive that?
It's hard to conceptualize.
The distances involved are staggering, and the gravitational shear forces of interacting galaxies must be incredibly intense. How does a tiny, low-mass star get ripped out of the Large Magellanic Cloud, pulled into into the Milky Way and just completely avoid being shredded by tidal forces or swallowed by the chaotic center of our galaxy?
It's a great question because it feels intuitive to imagine galactic interactions as these incredibly violent, chaotic collisions, like two solid objects smashing together at high speed with sparks flying and total destruction everywhere.
Like car crashes in space.
Right. But we really have to recognize the sheer terrifying scale of empty space within a galaxy. The distance between individual stars is so vast that the physical volume of a star itself is practically a rounding error compared to the void around it.
So they don't actually hit each other.
Almost never. When galaxies interact or when the Milky Way strips material from a satellite galaxy like the Magellanic Cloud, the stars themselves do not collide. They essentially pass through the opposing galaxy's structure like ghosts.
Like ghosts just passing right through.
Exactly. The interactions are purely gravitational. The Milky Way has an immense dark matter halo and a massively deep gravitational well. So as a Large Magellanic Cloud orbits us, the gravitational gradient of the Milky Way pulls on the side of the cloud closest to it with slightly more force than the far side.
And that stretches it.
Yes. This differential pull creates what we call tidal shear. Over hundreds of millions of years, this shear gently strips streams of gas and stars away from the smaller galaxy.
Wow. It's literally galactic cannibalism, but like very slow cannibalism.
Very slow. Our star was simply caught in one of those tidal streams. It wasn't violently yanked. It was slowly, gradually drawn out of its local orbit within the Magellanic Cloud, and it entered a new elongated orbit, just falling into the gravity well of the Milky Way.
But the star itself isn't torn apart by that pull.
No, because the star's own internal gravity, the very force maintaining that hydrostatic equilibrium we talked about earlier, is vastly stronger than the external tidal forces gently pulling at its surface. So the physical structure of the star is entirely unbothered. It just sails smoothly along the curvature of space-time, quietly transferring from one galactic host to another.
The mechanics of that journey are just staggering to think about. A drop of distilled water from the dawn of time, surviving a 13 billion-year wait, only to be ferried completely intact across the void of space into our cosmic backyard.
It's poetic, really.
It is, and the fact that we were able to detect it, analyze its chemistry down to a fraction of percent, and trace its orbital history backward, it brings us to the human element of this deep dive. Which is maybe the best part, the realization of exactly who was sitting in the control room when this data came down from the Magellan telescope.
Yes, because the scientific discovery itself is profound. But the sociological context of how it happened, that is what makes this a real landmark moment for astrophysics education.
Because the data wasn't cracked by, an isolated team of tenured professors working in a locked lab for 5 years.
No, it wasn't. It was the ultimate college spring break trip.
Alexander G., a professor at the University of Chicago and a former postdoctoral fellow at Carnegie Observatories, brought a group of his undergraduate students to the Las Campanas Observatory in Chile. This was quite literally the fieldwork component of his class in astrophysics.
We really have to set the scene to understand the impact of this for those students. The Las Campanas Observatory sits at an altitude of nearly 8,000 feet in the Atacama Desert.
So the air is thin.
Very thin. The air is incredibly dry, the atmospheric seeing is among the absolute best on the planet, and you are surrounded by some of the most sensitive, advanced optical instruments ever engineered by humanity. For an undergraduate student, just being physically present in that facility is overwhelming.
I can imagine. On their first night on the mountain, they visit the DuPont telescope. And they are really just observing the observers. They watch the technicians running the SDSS survey, taking in that wide net, low-resolution data, filtering the haystack. It's essentially an observational tutorial.
A warm-up.
Right. But the very next evening, the undergraduates actually transition to the 6.5-meter Magellan Clay telescope. They step up to the plate.
They were utilizing the mica shell spectrograph, specifically targeting the anomalies flagged by the SDSS data. And the process of raw data reduction in real time is intense.
What does that actually look like?
Well, when the CCD sensor reads out the data, you don't instantly see a clean graph on your screen. You have to subtract the electronic noise of the sensor itself. You have to remove the atmospheric telluric lines from Earth's own atmosphere, flat field the image, and then carefully calibrate the wavelength pixel by pixel.
And the students are in the control room doing this computational heavy lifting in the wee hours of the morning.
Exactly.
Most college students on spring break are engaged in entirely different chemical analyses at 3:00 a.m.
Yeah, fair point.
But these undergrads are running the reduction scripts. They pull the calibrated spectrum up on the monitor. And they see the physical evidence staring back at them.
They are looking at the specific wavelengths where elements normally absorb light. They check the 3933 angstrom line for calcium. They check the G-band for molecular carbon. They look at the dense cluster of iron lines around 3859 angstroms.
And what do they see?
Instead of seeing deep, prominent absorption troughs, they see continuum. They just see a nearly flat line. The metals simply aren't there.
In real time, at 3 a.m., they verify that they are looking at the most metal-poor star ever recorded, a 13-billion-year-old cosmic fossil from another galaxy. And the reaction from Professor Alexander G, honestly, perfectly encapsulates a massive shift in how astrophysics is being taught right now.
It really does. Juna Kohlmeier, who directs the SDSS project, champions a very specific pedagogical philosophy. She argues heavily against the traditional model, where undergraduate science basically consists of repeating centuries-old lab experiments where the answer is already printed in the back of the textbook.
Which is how most of us learn in science.
Right. But with the sheer volume of high-quality data being generated by these automated surveys today, she advocates for what she calls a curriculum of discovery. The philosophy is that students should be thrust directly onto the bleeding edge of science, working with raw, unanalyzed data where actual breakthroughs are a structural expectation, not just a weird anomaly.
And Alexander G lived that philosophy right then and there. At 3 a.m. in the control room, once the discovery was confirmed, he didn't just log it in a notebook and move back to the planned syllabus for the next day.
No, he threw the syllabus out.
He threw it out. He completely reconfigured the remainder of the semester's coursework around this single discovery.
Because he seized the moment to teach the most critical, unteachable skill in the scientific method: flexibility. When the data presents an anomaly, you abandon your preconceptions, drop the rigid schedule, and you just follow the empirical evidence wherever it leads.
That's real science.
It is. The students spent the rest of the term analyzing the stellar atmosphere models, running the nucleosynthesis yields, and actually drafting the peer-reviewed findings.
Imagine stepping back onto campus after that spring break. The quintessential college experience of returning to the dorms, and when someone asks, "Hey, how was your trip?" You have to casually explain that you spent the week fundamentally rewriting the bounds of early galactic nucleosynthesis and identifying an ancient extragalactic immigrant star hiding in the Milky Way halo.
It's quite the icebreaker.
It bridges the gap between incomprehensible cosmic scales and tangible human curiosity.
And it creates a self-sustaining loop of scientific inquiry. By placing undergraduates at the helm of a 6.5-meter telescope and allowing them to experience the visceral shock of unfiltered discovery, you cement their trajectory in the field forever.
Bro.
They aren't just passively learning astrophysics. They're actively generating the astrophysics that subsequent generations will study.
The oldest, most pristine matter in the known universe, being untangled and decoded by the youngest, newest generation of scientists. It's a profound synthesis of time, technology, and human drive.
I couldn't have said it better myself.
I mean, just look at the journey we've taken today. We started 13.8 billion years ago, navigating the opaque superheated plasma of the epoch of recombination. We tracked the thermodynamics of the first massive population 3 stars, watching them wage a losing battle against gravity without the cooling aid of heavy metals.
And we saw their rapid, violent demise forge the first trace elements in the universe.
Right. And from the localized shockwaves of those first supernovae, the mechanics of star formation shifted, allowing lower mass stars to form and survive. SDSS J0715-7334 condensed out of that ancient debris, locking an impossibly pure, low-carbon, low-iron chemical fingerprint into its atmosphere.
We traced its gravitational dynamics as it formed in the Large Magellanic Cloud, only to be ensnared by the immense tidal forces of the Milky Way.
Slowly spiraling across the intergalactic void via dynamical friction to settle quietly into our own halo, and we witnessed the massive interconnected architecture of modern astronomy required to even find it.
The statistical dragnet of the Sloan Digital Sky Survey.
The robotic fiber positioners, the micro-arcsecond astrometry of the Gaia satellite mapping its kinematic orbit, and the sheer resolving power of the mica shell spectrograph on the Magellan telescope, overlapping high-resolution light waves onto a 2D sensor to measure elemental abundances down to the milliangstrom. All of it culminating in a control room in the high Chilean desert with a group of undergrads.
It forces a massive paradigm shift in how you view the night sky. The light hitting your retina isn't just a spatial map, it's a temporal one. You are looking at layers of cosmic time existing simultaneously.
Like looking down a time tunnel.
Exactly. The discovery of SDSS J0715-7334 provides empirical validation for our hydrodynamic models of early universe nucleosynthesis. But more importantly, it proves the limitations of our current models, particularly regarding carbon cooling. It proves that the structure of the cosmos still holds fundamental anomalies that defy our expectations.
Which brings us right back to that perfectly preserved Model T Ford idling on the neon-lit superhighway. It survived the chaotic restructuring of a galaxy hiding right in plain sight. If a low-mass, 13-billion-year-old star forged in a completely different galaxy can survive tidal stripping and migrate into the Milky Way perfectly disguised among billions of heavy metal descendants, what other kinematic ghosts are out there?
That is the million-dollar question.
What impossible anomalies, rogue stars from entirely dissolved satellite galaxies, or remnants of the very first epoch of light are currently sailing right above our heads, just waiting for the right telescope and the right curious mind to finally look closely enough?